Good day, I'm Lugaz from University of New Hampshire, and I'm going to talk to you about shocks inside coronal mass ejections, focusing on two aspects, the geo-effectiveness and the acceleration of particle. So let's start with fast forward shocks at 1 AU. Emilia Kinpua and our group from the University of Helsinki have developed a database of shocks measured near 1 AU, including stereo ACE wind discovery with well over 1,200 fast forward shocks right now. And it lists the shock speed, the Mach number, and we would expect a relatively simple relationship between the shock speed and its Mach number, which is typically derived from the shock speed. And it is actually true. You can see in this graph showing for all these about 1,000 shocks, Mach number versus the shock speed. It's not necessarily a linear relationship as we'd expect, but you also see, especially in this grid ellipse, which are shocks which are faster but relatively weak. It's not really typical shocks. And we look, what does this shock come from? Well, what happened is they actually propagate inside low plasma beta regime, fast upstream condition, and fast upstream alpha speed. So this weak fact shock, when you look in details, there are shocks propagating inside coronal mass ejection, which is what I'm going to talk about now. This is my cat. So how often do you see this type of shocks inside coronal mass ejections? It's actually work also done 10 or 20 years ago, including by Collier et al. What we did here in a study in 2015, published in GDR, is we identified all the shocks propagating inside coronal mass ejection in source cycle 23, identified about 50 of these shocks. A few things here. You can see that's the number of shocks in blue versus the year, and that's the number of CME. So it clearly follows solar cycle dependency with more shocks inside CME in solar maximum, which makes sense because to have a shock inside a CME, you need to have multiple CMEs, typically. Preceding one and a one faster one can catch up and have a shock propagate through it. 70% of these shocks propagating through CME quasi-perpendicular, which also is consistent with the previous study by Richardson and Kane in 2010. And if you look at the statistics, we found about 15% of CMEs have actually shocks inside them, whereas about 15% of shocks are propagating through a previous coronal mass ejection. We also looked a bit at the conditions, the compression ratios, the Mach number. What we found is that these shocks are indeed weak in terms of the Mach number, but they're fast, and they still are pretty compressive. So here's actually one of my favorite examples in September 30, 2001, showing coronal mass ejection, ejecta between these two blue lines, and the solid red line is a shock towards the back of this coronal mass ejection, propagating through it, showing the density, velocity, temperature, magnetic field, its component, and some coupling function. So we can see what's special about this shock is that while it's faster, its speed is about 700 km per second, while it's faster than the back of the CME, it's clearly not faster than the front of the CME, which means this shock is never going to be able to propagate through all the way to the front of the coronal mass ejection, which is why, and the reason the shock is at the back. And actually what we found statistically is that the majority of shocks in the coronal mass ejection are in the back third of the CME ejecta. And so it's not just because of Earth's position, but also probably because some shock will not survive through the propagation of this one, partially because the speed that it sees upstream is increasing, partially also because the alpha speed that it sees is also increasing towards the center of the cloud. What do we care? Well, in a follow-up study in 2016, what we did is we looked at all shocks and sheaths at 1 AU, which were able by themselves to cause at least a moderate geometric storm in terms of DST less or minus 15 Tesla, irrespective of what drives this sheath. So it might be a superstorm after it, or it might be nothing. I don't care. I only care about the sheath region itself is able to create moderate geometric storm. What we found, there was 94 shocks and sheaths which were able to create these conditions over 20 years, from solar cycle 23 to pretty much the max of 24. Look in more detail, found that about half of these shocks are actually shock propagating through previous coronal mass ejection, whereas about the other half is propagating through typical condition, what I call normal shocks. And then we look in more detail too. We find that, for example, here in blue, this is the DST peak. You can see that typical shocks inside the coronal mass ejection actually lead to an intense dramatic storm, whereas a typical shock inside a normal solar wind condition only drive a moderate storm. In more detail too, since we know that only about 15% of shocks are propagating through previous coronal ejection, we see that half of the total shock which are effective are some of these. So clearly, shocks in that transition are statistically more likely to be effective, and quite so. In fact, about half of shocks inside coronal ejection will lead to sheaths that are effective, about 10 to 15% of shocks in typical conditions. And again, looking a bit more detail, and a beautiful example from September 2012 and October 1st, here is so two shocks from the red line, the second one of which is propagating through a weak coronal mass ejections here, showing the magnetic field, the component, the density, the velocity, the CMEs in black, or GST if you want, and the AL index for substorm, and the metropause location as derived by the Schwed al model, as I'll explain in a second. So what happened with this? Actually, what we find is that the typical coronal mass ejection, when you hit Earth, you have really two things. The sheath compress the heliosphere, and then maybe 10 hours later, when the ejecta start, the reconnection start, and you start to have substorm and a dramatic storm. When you have a shock inside a coronal mass ejection, which happens here, what you see is that at the same time, density and velocity increase, so dynamic pressure increase. At the same time, you get a strong magnetic field increase. So these two things happen at the same time. You have simultaneous compression and reconnection happening. Now that actually is perfect to really push the metropause all the way to a very low region, in this case to just circumference orbit. And what we show here is actually the effect of the combined erosion and compression, the normal Schwed al in black, and just the effect of the compression. So you can see here, it's not just a compression, it's really a compression and an erosion that pushes the metropause to geosynchronous, which is really perfect condition for metropause shadowing and strong radiation belt losses. I could read more about this event in a couple of papers listed here. And actually this event, if you're from radiation belt community, you know this event because that's pretty much the first strong radiation belt losses in the outer belt of the RBSP, or fundamental probes area. I have a quote here from actually a science paper talking about this event, which is here. There's this huge drop in energetic electrons in the outer belt. And really, it's not anything special in the strong shock. It's really because this shock is propagating superverse coronal mass ejection. And this thing, which is relatively weak shock and weak eruption, actually create conditions which are extreme in terms of radiation belt effect. In a Gerald paper of 2015, we actually study a bit more detail of this, but to emphasize again, a few things are important is that you take a weak shock, typically here in 450 km per second shock, that's a pretty weak shock at 1 EU, a moderate shock, and a weak coronal mass ejection, and you get conditions that combine the compression and erosion really are extreme in terms of the metropause location and the radiation belt. In this case, you can see that the radiation belt were pushed to pretty much geosynchronous orbit for 5 hours, in large losses as measured by GOES of the energetic electron fluxes at geosynchronous orbit. Again, this simultaneous effect of the compression by the dynamic pressure and the erosion by the BZ south in this case. So obviously, the shocks inside coronal mass ejection also been studied numerically. Back starting with Vandas in the late 90s, actually Ivanov into simulation, but really represented this pretty much the way we do now back in the 80s. Simulation that I did, simulation also I've done. A few things. From simulation, we know that indeed shocks can survive through coronal mass ejection, also their properties will change significantly, and it still remain compressive. Some of them will dissipate. Partially because one of the most nice recent event, which was the September 2017 event, was actually a series of 3 coronal mass ejection. One of which was actually a shock through previous eruption, which is shown here, with E1 being the ejecta 1 and shock 2 inside of it. You can see again this increase in the magnetic field, extreme increase in the magnetic field, really created the first drop in the DST of this event. So because of that, there's also more recent simulation. There's a paper by Scolini just a few months ago in APJ Supplement, Again, talking about the same three phases we described before, but here, kind of talking also about the importance of Earth's position for this exact interaction to occur at the time. And so actually similar to what Yinglu has been talking for a while, which is this idea of perfect storm. And really the idea is that somewhere between Venus and Earth is the perfect place for shocks to propagate through CME. At Mercury, we're gonna see series of CME don't interact. By Mars or beyond, you will see compound event where interaction has already occurred, but kind of at Earth's location is actually when interaction is still occurring. So you get these very extreme conditions. Again, I don't have time to go through all the groups, but many groups have worked in this. Some of us give different names. In particular, Yinglu calls this, I focus on the shocks, so I call this shocks inside CME, but if you focus on the CME, you actually call this a CME in the sheath, but really it's the same thing. Some of you are studying the same events, and studying different event. Again, 2017 is a very beautiful example of an ejecta compressed by a shock, ejecta 2 or 1. I'm going to move to a slightly different topic, as to the same phenomena, shocks inside CME, which is acceleration of particle. And in fact, back about 12 years ago now, Shangdong Shen et al. Reached a paper where they found that you see pretty high flux of KV to MeV particle at 1 AU when this shock and the CME passes, which is also a more recent paper by Zhu Mengjiao from last year. Just to emphasize, it's different from the twin CME scenario. I'm talking here about acceleration as the shock passes 1 AU, not in the corona. So let's look back at the same event. The one I love is September 30, same plot. I just added here the KV and MeV protons. And you can see that there is an enhanced level of energy particle. It doesn't start at the first shock. Again, this red line as a 2 shock. It starts fully at the start of the ejecta. So it's as if this shock, propagating superior CME, is able to fill entirely this previous ejecta with particle. And I think it's something interesting. So again, we ponder a bit. I looked a bit more. In fact, electrical storm particle event appear well studied. If you look at the database of RIMS from 2012, you find that 1/4 of his 39 events more or less are shock site CMEs, and nothing seems to be particular about them in terms of their fluxes or shock speed. Again, they are low beta plot, but nothing particular in the particle. So maybe we should look at this event and see if something happened. For example, do we see this place where the particle fill up the entire ejecta previous to the shock? And yes, we do. So here's some examples of strong shocks. Again, the same magnetic field, density, velocity, and the flux of particle. And you can see the shock here in blue. And throughout the preceding ejecta, you see this high level of particle. So it's not something that particles are bouncing between 2 shocks. It's really particles are filling up this closed film line of an ejecta. It happens also with shocks that we'll consider very weak, Mach 1.1, because again, the Mach numbers that you measure is not really the Mach number of the shock. It will depend on the upstream condition. So this leaves us with kind of a couple of questions. One is this kind of CME shocks inside coronal ejection inherently more efficient at extreme particle? And in fact, there's kind of 2 sub-questions. One is that, well, I can understand a closed film line, maybe also trap particle, and maybe reflecting them back without even the necessity of wave or turbulence, and then being reaccelerated, and so creating an efficient mechanism. However, which particles? An ejecta is made up of a very cold plasma, very low density, so it's not a place, and low turbulence. It's not a place we expect to have the seed particle necessary to accelerate it. So we tried to see what would happen with my postdoc generally in a paper just published pretty much in December of 2020. What we did is created a 1D situation where we have a reflective boundary at a distance L from the shock, which is kind of mimicking this closed film line, pushing the particle back towards the shock. However, there's some leakage, some field lines are open, or there's crustal diffusion, which allows some particle to exit as a time scale of tau. And then we just solve the time-dependent shock acceleration equation, where the key parameter really is the ratio of this distance of the boundary to the diffusion scale Ku over Vu. we do find that here's a solid line as a result for realistic value of this alpha versus a version where the boundary is at infinity, so this is pretty much non-boundary. And you can see that you can find more particle acceleration at low energy. So we can bump the particle maybe 20% by energy. Why not more? Because really there's no time. With this kind of distances, the shock is actually also pretty weak. You know, the upstream speed is only about 200 km per second at most in the Solon frame. So there's really no time and no strength to accelerate particle beyond. So while it's possible to accelerate particle, it's not enough to explain this flux of particle of hundreds or keV to MeVs. So what we think is a more likely scenario is that particles which are initially accelerated by the shock before the interaction are then being able to enter the preceding ejecta due to reconnection between two ejecta, as we see from simulations, and then are actually reaccelerated. So it's not just an efficient way, it's actually, we have particle being trapped inside the preceding ejecta through reconnection between the sheaths and the ejecta, and then reaccelerated by as a shock a second time. So kind of as a conclusion, I think I'm running out of time, but we looked at shocks inside previous CMEs. They're not uncommon, about 15% of shocks, 15% of CMEs of shocks, one of them. It's a great way to make a weak CME geo-effective, and really Earth is well positioned for this, which is something that both Camilla Scolini and Ying Liu have been talking about recently. And really, what I think is important is that it's characteristic by themselves actually efficient to create conditions perfect for medipose shadowing, for strong geo-effectiveness, especially in terms of radiation belt. We also talked about the acceleration of particle by such shocks near 1AU, found that while you can understand why the reflecting boundary can be an efficient way, and we actually did a theoretical conditionalization of this in an identical formula, there's really no time for the particle to be accelerated to high energy. So what is likely to happen is an alternative scenario we propose, Jenny and myself, which is the reacceleration of previously accelerated particles which have entered and been trapped inside this preceding ejecta through magnetic connection, reaccelerated by the shock. Thank you. Enjoy COSPAR.